Hi and welcome to this short clip introducing electron configurations. It's designed to go with your independent study notes on this topic, so you should have those to hand before you start. So we've got three simple dot-cross diagrams here, and they all represent atoms you've come across at GCSE. If you were to use the GCSE model to apply electron configuration, you'd just simply count up the number of electrons in each shell. So I'd imagine you'd come up with something like this. So what I'm going to do now is reveal the A-level version using what we call the orbital model. So at this point I'm assuming that you know what an orbital is, shapes of the S and P orbitals, and a little bit about how elements are grouped in blocks in the periodic table according to what orbitals are being filled in their atoms. Now if we look at the orbital model configurations, you'll see that there are big numbers and little numbers. So this orbital in the helium atom is in shell number 1, or what we could say energy level 1. And it's an s orbital with 2 electrons in it, each spinning in opposite directions. And this can be written as 2 arrows in a box. Notice the arrows pointing in opposite directions. So if we apply this to neon, obviously neon has more electrons, doesn't it? So remembering that an s orbital contains only 2 electrons, but a p subshell contains 3 p orbitals, so therefore contains up to 6 electrons, we can put the same arrows in. And we can also do the same for the argon atom. So far we've just looked at noble gas configurations where the p subshell is full. Let's look at some other ones where it's not. But before we do that, it's also worth remembering that orbitals and subshells are classified according to which energy level they sit in. So an energy level can be taken to mean a shell. So as far as possible in subshells, electrons will try to occupy separate orbitals so as to avoid repulsion. So in the example of oxygen, which is 1s2, 2s2, 2p4. So we can also write out longer electron configurations using shorthand. So the way we do this is we look for the nearest filled p subshell to the end of the electron configuration. So just that section, 1s2, 2s2, 2p6, is equivalent to the electron configuration of neon. So we could, if we wanted, write aluminium out as square brackets Ne to represent the 1s2, 2s2, 2p6 part, and then write outside that 3s2, 3p1. So this graphic shows everything we've talked about so far for potassium. So let's say we wanted to do the shorthand for potassium. You could write out the symbol for argon, because that's your 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. So if you're writing a electron configuration, there's a couple of things you can check as you go to make sure you're roughly in the right place. Does the sum of all the superscript numbers match the total number of electrons? And does the final letter in the electron configuration match the block the element is located in? So if we look at potassium, it's got 19 protons, so therefore it's got 19 electrons. Let's look at the electron configuration. And as you can see, the total number of electrons is 19. So that shows how we can check what we're doing. Does the final letter in the electron configuration match the block the element is located in? Well, potassium is in the s block, so therefore it should end in a s orbital, or an s subshell, or should have s at the end of its electron configuration. So let's wrap up with a few limitations of the shell model. Firstly, it doesn't account for the fact that p subshells sit slightly further away from the nucleus. It just assumes that all the electrons in one particular shell are equidistant from the nucleus. That's not quite true. The version taught at GCSE doesn't account for the filling of larger subshells such as D or F, so when you start getting into the third shell and beyond, it's no longer good enough to say that the third shell has 8 electrons. It actually has a lot more than that if it's completely filled. So we still very much use the idea of shells, it just needs to be updated and refined a little bit, because we now have further evidence since the shell model first came into being that supports the subshells idea, that requires a new model to be put in its place. So just to recap and finish off, let's have a look at how we fill orbitals in which order. So we always start off with 1s. Once the s orbital is filled, you start to fill the p, then the d subshells. As you can see, F comes after D, but we don't really deal with F orbitals or subshells at A level. And the shells must be filled in strict order of increasing energy, so we start with shell 1, then shell 2, then shell 3, until, of course, we run out of electrons. Okay, so hopefully that's a reasonably easy to understand introduction to electron configurations and how they're constructed. Now it's time to go and practice some. Thanks for listening, and see you soon.